everyone. My name is Shi. I'm from Duke University. And today I'm going to present a talk composing differential privacy and secure computation, particularly on a case study on scaling private record linkage. So this is a joint work with my advisor, Ashwin, and Cheryl Devash from AT&T Labs Research. So first, let's take a look what is secure two-party computation. So given two parties, Alice and Bob, each of them have a private data, respectively A and B. And they want to compute the value of public function on that private data, let's say FAB, while keeping their own input secrets. So for example, this function can be is A greater than B or is A similar to B. So this problem have many interesting applications. One important application is called private record linkage. So, for example, in a collaborative study, let's say two hospital A and hospital B, they want to find the common patients that exist in their database, but their primary keys may not necessarily be the same. So you have to use a matching rule to determine whether a pair of records are a matching pair or not. So this matching rule can be very simple, can be a distance-based matching rule, or it can be very complex, such as complex classifier. And the privacy constraint here is hospital A should only learn the matching outputs, the matching patients between these two hospitals, and the input data size of the opposite party, but nothing else. What does that mean? Means that, for example, this person, the red person, does not exist in hospital B, right? But it does not exist in the matching output between these two hospitals. So hospital A should not know the presence or absence of this person in hospital B. And this problem can be solved using secure multi-party computation. The baseline is you can securely compare all pairs of A and B from D and DB based on the matching rules, right? Such as using gobble circuits or homomorphic encryptions. And using this method, it guarantees a very strong privacy guarantee, recording indistinguishability based S2PC. We're going to define this definition later on. And here we assume semi-honest and computationally bounded adversary. However, using this protocol, all pairwise comparisons can be really slow for complex matching rule. So suppose each of them having 1 million records, and it will take 10 to the power of 12 number of secure pairwise comparisons. And for complex classifier, let's say it takes 1 millisecond for one secure pair comparison, 1 millisecond, and total takes 31.7 years to finish, right? There are some efficient techniques, such as efficient power setting sections, that can be applied to this problem, but only for equality-like rules. But if you want to deal with more general matching rules, such as complex classifier, right, this method may not necessarily applicable. So there's some prior work to say, yeah, we can speed up record linkage using blocking. How about using the same technique to speed up private record linkage? So what does it mean by blocking? I will give you two examples here. So giving you having 4 people from each hospital, and you apply a hashing function to map these records into here 3 bins, right? And then you can have secure comparisons between the records from the corresponding bins. And we can see that this approach reduces the number of secure pairwise comparisons from 16, right, to only 4. So this is a great reduction in the number of secure pairwise comparisons. However, right, this approach actually have some leakage of information. So I leave this as an exercise for the audience to figure out. But the intuition is that by changing some record values, the number of secure pairwise comparisons in total will be affected, which is part of the view of the adversary. So that information will help the adversary to distinguish between some database. So how about differentially private record blocking, right? We have heard a talk just now, what is differential privacy? It's very strong. And how about apply differential privacy in this case? So the key idea is to join noise from Laplace distribution for each bin. If the noise is greater than 0, you add dummy records to that bin. If it's negative, right, you suppress corresponding number of records. And this way, you still can compare noisy records from the bins, right? This approach still gives you reasonable good reduction in number of secure parse comparisons. So this is some key idea. We're going to use this approach to speed up PRL. So our goal is that to design a protocol for perfect linkage that satisfy all three desiderator. First, correctness. You want output most of the true matching pairs between these two databases. And the second desiderator is we want to provide end-to-end probable privacy guarantee. And third desiderator is want to achieve subquadratic communication and computation costs in input data size for problems with subquadratic outsize. Okay. And one of the key and interesting questions is how to provide end-to-end privacy guarantee for the composition of differential privacy and secure multiparty computation. And the answer is not always trivial. So here are two differential private implementations to speed up PRL. I won't give you a chance to look at the details, but I will tell that one of them doesn't work. Okay. So in our talk, we're going to answer these questions. Firstly, in the first part of my talk, I'm going to propose the protocols to achieve these three desiderator: correctness, privacy, and efficiency. And in my second part of my talk, I'm going to provide an end-to-end privacy analysis for this hybrid approach. So first, let's take a look what is differential privacy. We say a mechanism satisfies epsilon delta differential privacy if for any output O and any neighbors D and D prime differ in one record by adding a removing record from D. And output distribution for these two databases, D and D prime, should be similar. The probability to generate the same output from D and D prime should be bounded by e to the power epsilon with some epsilon negligible term of failure. So here we see that D and D prime in the example here having one record missing 5, right? And we're going to show example how to ensure differential privacy here, which is Laplace mechanism for counting query. Laplace mechanism can join noise from Laplace distribution, usually from a distribution with a 0 mean and parameter S over epsilon to the query. And this way you can satisfy epsilon 0 differential privacy, where S is the sensitivity of the query, which bounds the maximum change of the query outputs when you're adding and removing a record. So here we see we have two databases, D and D prime. D have 3 records and D prime have 2 records. And if I want to ask the query, how many 4s appear in this database and how many 5s appear in this database, right? The answer for these two databases are 1, 2 for D and 1, 1 for D prime. And then we can draw some noise and obtain the same output. But the probability to generate the same output is going to be different. But the difference between them, the ratio between them, should be bounded by e to the power epsilon. Okay, so based on this idea, we propose our Laplace protocol. So we draw noise alter from Laplace distribution for each bin. But the mean of this distribution is going to be greater than 0. It depends on the sensitivity, epsilon, and delta. Okay? And if the noise is going to be greater than 0, then we add corresponding number of dummy records into that bin. If it's negative or 0, we don't do anything. So you can see why we want to add to consider distribution with non-negative mean. So the probability to draw a negative noise is going to be small, which contributing to some negligible term. And after we create these noisy bins, we have secure multiparty computations between those noisy bins. So this is a summary of the entire protocol. And for the first part of the protocol, it's trivial to see that it satisfies epsilon delta differential privacy. And the second part satisfies the original strong privacy guarantee on indistinguishability based S2PC. And we can show both theoretically and empirically that this approach can obtain high recall, as it outputs as many matching pairs as the approach without adding any dummy records, right? And for efficiency, this approach also remains subquadratic. If the approach without adding dummy records is subquadratic in the input data sites, and number of beans is subquadratic, and each bean of the party is compared with constant number of beans from the opposite party. So in the literature of record linkage, such blocking function is not hard to find. So this is one small sample of the evaluation result we got. We're matching records which are product names and time from about.com and by.com. So we want to evaluate the scalability of different protocols. So increase the data size here by increasing T from 1 to 16. And the cost here evaluated is based on the number of secure pairs comparisons or number of operations over encrypted values. So we have two baseline. One is private set intersection with expansion. So this approach will expand one of the data sets such that all the matching records of one of the records in DA should be included. So using this expansion method, we can obtain high recall, even though the matching function is not equality-based. And the second baseline is all pairs comparisons. And for Laplace protocol, evaluate different epsilon values 0.1 to 1.6. And this NP approach will correspond to the approach that we don't add any dummy records. And we can see that the first baseline, PSI plus X, by expanding one of the data set, can incur high costs because of the matching function and the dimensionality of the data sets. The expanded data size can be really large. So this causes the high cost. Even though the private set insertion method itself is efficient, you can see that the gradient of this approach is still close to linear. And for the second baseline, all pairwise comparisons, right? But this approach also incur high cost. And most importantly, the gradient of this line is 2. So we represent to quadratic cost. And for the rest of these approaches corresponding to Laplace protocol, but with different epsilon value. The epsilon value increases from 0.1 to 1.6, and we can see the lines are shifting downwards, and all of them have a gradient near linear. So when the epsilon increases, it corresponds to a relaxation in terms of privacy. And the lines getting closer to NP protocol, where you don't add any dummy records. So there's a trade-off between efficiency and privacy by adjusting epsilon. So it's nice to see this protocol can achieve high recall and subquadratic cost. But the question is, what is the end-to-end privacy guarantee, right? You see, the first part ensures epsilon delta differential privacy, and the second part ensures a strong notion called indistinguishability S2PC. So what is the end-to-end privacy guarantee? That comes to our second part of this talk. Okay. So firstly, let's take a look what is S2PC for this case. So this is a formal definition, but I just want you to focus on the neighbors here, which correspond to for any DA, and we say DB and DB prime are neighbors if the function output FDA DB equals to FDA DB prime. In the application of PLL, this function corresponding to the input data size of each party and the matching pairs between DA and DB based on the matching rule N. And so given DA, and consider Alice as the adversary, right? DB and DB prime are neighbors if they have the same matching pairs and they have the same data size here. And the views of Alice should be indistinguishable from DB and DB prime. And this view includes Alice's own records, the internal randomness in her protocol, and the messages seen by her. So this seems not very clear, right? We actually apply a method to present neighboring databases as a graph. So this helps you to see how does this work. In this graph, we use V to present all possible databases, and the edge connect neighboring databases. So for PRL, DB and DB prime are neighbors if they have the same data size, and the matching rule, the matching output are the same. So using example, if you consider a record domain from 1 to 6, and DA have two records, 1 and 2. And this is part of these graphs. And we see 1, 2, and 1, 3 are disconnected. There's no edge connecting between them, okay? Because 1, 3 has one matching pair with DA, which is 1, 1. And for 1, 2, you have two matching pairs with DA, 1, 1 and 2, 2, right? So the output for these two databases with DA and this function are different. And how about another pair? Let's say 3, 4, and 5, 6. So they're connected by an edge, right? But they have a lot of difference. But the reason for them to be connected because they have no matching output with a given DA, right? So this gives a very nice view how neighbors looks like. Now how about differential privacy? Record that the neighbors of differential privacy is formed by adding and removing a record from D. So take the same domain, 1 to 6, and this is a part of the graph to present neighboring databases. And see here, database 1 and database 1, 2 are connected by edge because by adding and removing 2, you can get the opposite, get another one. And the distance is 1, and the probability for the verse to distinguish between them based on the same output is going to be e to the epsilon. And same apply for database 1 and database 1, 3. And if a pair of databases that are slightly further away, the probability to distinguish between them is going to be larger. And now you put these two neighboring databases graph together, right? You can see actually PRL and differential privacy protects different sets of neighbors. And taking the same pair of databases, they have different distance and different probability ratio, and similar for 3, 4, 5, 6, right? In differential privacy, their distance should be 4, but in PRL, their distance is just 1. So how to bridge this gap? So given these two different set of neighbors, so one idea is just to redefine neighbors with a given function. We call this F neighbors. And the definition is described as follows. DB and DB prime are neighbors with respect to given function F and DA. First, both need to satisfy output constraint, which FDA DB equals to FDA D prime. They have the same output. And the second condition is that DB and DB prime are different. And lastly, very importantly, DB and DB prime are minimum different in terms of record changes. So this set of neighbors actually have a stronger conditions compared to the condition for differential privacy and for PRL, right? And based on this definition, we can propose a new notion called output constraint differential privacy. I'm not going to present the definition here, but I'm going to use record linkage to illustrate the idea. So we say DB and DB prime are neighbors for the function when you compute under private record linkage. Firstly, they need to have the same data size, and they differ in only one non-matching record with respect to the given DA. So these conditions are derived from this F neighbor definition. And if we use the same example, record domain from 1 to 6 and DA equals to 1 to 2, this is the new graph where you can see that 3, 4, and 5, 6 initially connected by edge in the graph for PRL. Now they are disconnected, but they have a path of 2 to reach each other, right? So based on this definition, we can propose a new notion called differential private record linkage. So the key changes with respect to S2PC is that the neighbors are defined in the previous slide. And the probability to distinguish between them is bounded by e to the power epsilon b in this case. And same holds for the views of Bob with epsilon a and delta a. And the nice thing about this notion is also satisfy post-processing and sequential composition, which are nice properties about differential privacy. So this is the end-to-end privacy guarantee for the hybrid protocol we propose. And what's so nice about it? Firstly, this end-to-end privacy notion can help to evaluate a new approach. Remember, I showed two approaches in the beginning, right? And one of them, even though part of this protocol satisfy DP and another part satisfy indistinguishability S2BC, but it doesn't satisfy DPRL. Okay. And the second thing is if you want to propose a new approach, we don't have to go through all the process. We just need to show it satisfies this end-to-end privacy guarantee. This is one of the optimization steps we propose in the paper. It's called greedy match and claim. So Alice and Bob can greedily match records in clear in their own perspective after certain iterations and adding new matching records to the outputs. Interestingly, this step is not a post-processing step because Alice look at the true records. But we can use this end-to-end privacy guarantee to show that this step still preserve the privacy guarantee, right? And secondly, for the correctness, this approach also can capture some matching records missed by the blocking strategy. So if one record has multiple matching records, some of them are missed out because of the blocking strategy. If one pair have been identified, Alice and Bob can find those records in clear in their own perspective. And efficiency-wise, some of the secure parse comparison are replaced by these comparison in a clear, right? So this ensure the optimization step can improve the basic protocol. And this is one plot to show the optimizations. So here we have different bars, and each bar presenting optimizations or basic step. We just need to focus on the red bar, which corresponds to the Laplace protocol, which is the basic protocol, and the green bar corresponds to the basic protocol plus the optimization. So for these particular data sets, the reduction in cost is 16%. But this varies depends on data sites, depends on the data. Okay. So future work, right? It's going to be interesting to further investigate the practicality of this privacy notion. We would like to evaluate the work clock time in a specific operational environments, and also working with more real data sets with complex matching rules. And it's also be interesting to extend two-party setting to multi-party setting. So in this work, we explore PRL as the application for this general privacy notion output constraint differential privacy. It'll be really interesting to see is there any other applications. Last but not least, so this is one way to compose different privacy guarantees, right? How about other compositions? It remains interesting direction to explore. In summary, we propose a protocols that can achieve three desired correctness, end-to-end probable privacy guarantee, and sub-quadratic computational and communication cost. And we also see that it's not always trivial to compose DP and SMC. And we propose these new privacy notions to ensure end-to-end privacy guarantee for the protocols we propose. Okay, that's the end of my talk. Thanks very much.
So, I mean, differential privacy has a nice composition feature. Here also, you would get the same composition feature. Like if I do a set intersection with one person and then with another person, my privacy degrades nicely.
Is your question mean if I have a differential private protocol, does it compose with this definition?
Yes.
Yes, the answer is yes. We have shown that differential privacy and S2BC is a stronger notion than this DPRL notion or output constraint notion. And that's why we can actually compose that. But the composed results is definitely not differential privacy anymore, because you compose a stronger with a weaker one, you still get a weaker one. Does that
I'm
make
just saying
sense?
composing your protocol twice. It's not like composing like a DP mechanism with yours. I'm just saying doing your protocol, I do the protocol with one person and then with another person.
If it's a sequential composition,
Yes.
the answer is yes. Yes.
So your matching function in this work is just equality, right? And you mentioned that it's part of future work to see how we can extend it to more complex matching functions, right? Is this correct?
The answer is yes and no.
Okay.
So for this work, we aims for more complex matching functions, but in the evaluation, due to time constraint, we just work on some conjunctions, but not necessarily equality functions.
Mhm.
Yeah.
So in your blocking, I didn't quite understand. So I think it was one of your first slides, maybe 6 or 7 or something. So I didn't. If you could maybe go to that slide 6 or 7.
Oh, you mean slide 7? 6
Yeah.
or 7? Okay. Maybe.
6, I guess.
6.
This yeah. One? So yeah, I didn't quite understand how you do the blocking. So like, why the blue guys end up in the same like block, like on both sides? Is this just for illustration, or like in practice? I would assume you can kind of coordinate between those parties, right?
Right. That's a very good question.
Mhm.
So blocking in general means that you want to hash the records that are similar to the same bins. So one typical example that we mentioned in the paper is called locality sensitive hashing. So if these two records are very similar, they have higher probability to be hashed into the same bins. So given our blocking function, it's not necessary to capture all pairs of matchings, because there's still some probability they don't match into the same bins. Okay, hope that answered your question.
All right. Yeah, definitely. So, okay. So if there are no more questions, let's thank the speakers one more time, and please go and enjoy the coffee break.